mission today is, I think, laser-focused. We
Mm.
want to unpack how these sophisticated ML and DL techniques, the algorithms you read about, actually translate into functioning deployed systems. We're going beyond the theory. We're
Right.
talking architectural decisions, performance trade-offs, and why a certain model gets chosen for, say, high-speed manufacturing versus advanced medical
And I
diagnostics.
love that. We need to deliver actionable insight, not just definitions.
Sure.
Okay, so let's unpack this. We're going to start with the core toolkit, and not just what a CNN is, but why you'd use things like transfer learning.
Or ensemble methods,
Yep.
right?
Yes, exactly. Then we're diving straight into the hard data. We've got performance metrics for computer vision, and then we'll get into the architectural demands of Industry 4.0 systems, specifically edge computing.
Let's do it. For our engineer listener, let's just quickly set the landscape. We always differentiate machine learning, ML, as the broad field, and then deep learning, DL, is its highly specialized subset.
And DL is all about those deep neural networks, the DNNs.
Right. It relies on them. And they use multiple hidden layers, which is
Mm.
crucial because it allows for this hierarchical learning and, I think most importantly, automated feature extraction. We call it representation learning.
So the DL model basically figures out the important features on its own.
That's the core difference, yep. And when you look at the sources for modern engineered systems, especially in computer vision, the workhorse is the convolutional neural network, the CNN.
Yeah, it comes up again and again. As an engineer, you probably know the structure. Convolutional layers, ReLU, pooling, and the fully connected layer for the final classification. But let's focus on the engineering decision points in there.
That's a great pivot. I mean, why does the pooling layer matter so much in a deployed system? It's not just about saving computation time, though that's a huge factor.
Sure, efficiency is key.
But the pooling layer, through something like max pooling, it performs downsampling that intentionally prevents overfitting and, critically, ensures translation invariance.
Okay, so what does that mean in, like, a factory setting?
It means your system recognizes a defect or an object, even if it's shifted slightly on the conveyor belt. The positioning might not be perfect every single time. It's all about building robustness right into the system.
And that robustness is often challenged by data, right? I mean, you often don't have a million perfect labeled images for, say, a very specific type of cancer cell or proprietary machine part.
Exactly. And that's where transfer learning becomes, well, non-negotiable. It's an approach that solves that small data set problem by leveraging a model that's already been pre-trained on a huge general task, like object detection on ImageNet.
Ah, so you're basically borrowing the intelligence.
You're transferring that foundational visual intelligence to your specific domain. It saves an enormous amount of time and data collection effort.
I love that. So if transfer learning is about leveraging past knowledge, then what about ensemble learning? Is that like distributing the risk across multiple experts?
That's a perfect way to put it. It really comes down to complexity, noise, and dimensionality. When you're dealing with high-dimensional data that is, noisy or imbalanced, which is super common in industrial sensor data.
Or security applications?
Or security, right. A single complex model might overfit or just miss the nuances. Ensemble learning combines multiple weaker learners like decision trees or SVMs, and it harnesses the diversity of their predictions to get a superior, more stable result.
Speaking of nuanced data, our sources also brought up fuzzy systems. We usually think of ML as being, binary or probabilistic. Where does fuzzy logic fit in for something like lunar crater detection?
Fuzzy systems are essential when you hit data that's inherently ambiguous or imprecise. Think of visual data with sensor drift or bad lighting. Fuzzy logic lets variables take on degrees of truth, not just true or false.
So a crater's edge isn't a hard line.
Exactly. It's somewhat a crater and somewhat background. By integrating fuzzy logic with deep learning, engineers can handle that ambiguity, which bridges the gap between sort of human interpretation and rigid computation.
Of course, none of these amazing algorithms matter if your input data is garbage. Data preparation is everything. We're talking cleaning, aggregation, transformation.
Normalization, scaling, all of it. But for the engineer facing these huge data streams, efficiency means dimensionality reduction.
Absolutely.
Take the stress detection models we looked at. They used physiological sensors generating massive, complex data sets. In that case, they used principal component analysis, or PCA.
What's the core benefit there?
PCA reduces the dimensions while mathematically ensuring that the maximum amount of variance, the meaningful signal, is captured. It's not just for efficiency. Many classic ML models perform way better and are more interpretable when their inputs are standardized and uncorrelated. PCA helps you get there. It just cuts the noise.
Okay, So we've got the toolkit. Let's move into actual applications, starting with computer vision, where deep learning has really, just exploded.
It really has.
Yeah.
Let's look at a high variability task first. Hand gesture recognition.
Which sounds simple, but I'm guessing it's not.
It's a really complex engineering challenge. The goal is to interpret dynamic hand movements for sign language or, non-contact human-computer interaction. The tools are there, Python, TensorFlow, OpenCV. But the core challenge is handling the massive variation.
You mean like pose orientation?
Exactly. Pose, orientation, position, scale. A hand gesture looks completely different depending on the camera angle or the distance. The system has to generalize across all of that instantly.
Okay, now let's raise the stakes even higher. Medical imaging. The source is detailed as cervical pap smear classification system. This isn't just classifying an image, is it? It's about micro-level precision.
Precision is everything here. In a high-stakes environment like that, segmentation is the top priority. You have to precisely separate the cell nucleus and cytoplasm from the background to classify them correctly.
And how do they do that, especially when the samples aren't perfect?
They use sophisticated active contour models with something called local Gaussian fitting energy, or LGFE. LGFE is necessary because cell samples often have what's called intensity homogeneity, meaning the staining isn't uniform.
Ah, I see.
So LGFE helps the algorithm find the nucleus and cell borders accurately, even when those boundaries are blurry or the staining is inconsistent. It's a very specific engineering solution for a pervasive, real-world problem.
This is exactly the level of detail an engineer needs. But okay, the ultimate test is performance. Let's talk numbers. Our sources had some fascinating comparison data for malicious QR code detection.
Yes, and this is a great example of model selection based on the data. The random forest algorithm achieved an 81.46% accuracy.
Which is good, but why is it significant?
Because it just blew the others out of the water. The nearest neighbor was down at 71.61%, and a standard decision tree was at 76.76%.
That's a big gap.
It's a huge gap. Random forest, as an ensemble method, just excels at handling the kind of high-dimensional, noisy feature sets you see in cybersecurity data. And in a security application, that 10-point difference is massive in terms of false positives.
But if you want to see pure deep learning muscle in action, the face mask detection case study is the benchmark. Using a data set of over 10,000 images, the CNN model hit an accuracy of 98.57%.
Just think about that. 98.57%. That level of precision, approaching near-human performance, is the key metric that lets a DL engineer confidently say, okay, this is ready for real-world deployment.
Absolutely. Okay, let's shift focus now to these really complex operational environments, where ML is the engine for Industry 4.0, integrating with the Internet of Things and cyber-physical systems.
This is the heart of it all. This integration isn't just about collecting data. It's about automated, AI-driven decision-making that can save companies massive amounts of money.
And the most obvious gain there is predictive maintenance.
Predictive maintenance completely changes the game. It moves you from being reactive or just scheduled to being prescriptive. Sophisticated ML models consume all the sensor data, temperature, vibration, acoustic signatures to predict the remaining useful life of a machine.
So you prevent unplanned downtime.
You minimize it. And that can cost millions per hour in some industries. It's a huge economic driver.
And beyond just repairs, AI is also tweaking the production line itself through smart manufacturing and optimization.
Correct. Imagine AI frameworks trained on years of historical production data. They can dynamically make real-time adjustments to physical parameters, machine speeds, material flow rates to prevent bottlenecks and align output with fluctuating demand.
Which leads right into quality control. We're moving way beyond simple visual inspection here.
Oh, way beyond. AI-empowered visual inspections are meticulous, and they are tireless. You train deep learning models on these vast data sets of perfect units and every known defect, and they achieve a precision that is just impossible for a human inspector to maintain over an 8-hour shift.
Okay, so when you have millions of sensors on a factory floor, just pumping out data constantly, you immediately hit bandwidth and latency problems. Which brings up a critical architectural decision, edge computing.
Edge computing is the paradigm shift that moves the computation and data storage closer to where the data is actually generated, at the network's edge.
Right.
It solves a fundamental engineering problem. You can't send petabytes of raw high-frequency vibration data up to the cloud and get a response back in time to stop a catastrophic failure.
So you do the processing locally.
You deploy the inference models at the edge on a gateway device or the machine itself. And that just drastically reduces latency and bandwidth needs.
But that raises a big question about resources. When you move to the edge, you're sacrificing the, virtually unlimited power and memory of the cloud. What are the practical trade-offs an engineer has to make?
The trade-offs are intense. Edge devices are often severely constrained on power, memory, and processing. This forces the engineer to use model compression techniques like pruning or quantization to make the deep learning model smaller and faster.
So you might trade a tiny bit of accuracy for a huge gain in speed.
Exactly. You often accept a marginal trade-off in accuracy to get massive speed and power efficiency wins. The model gets trained in the cloud, but the edge performs that local, real-time inference and autonomous decision-making.
We've covered manufacturing, so let's look at a really specialized biometrics application. Our sources discuss detecting mental stress in housewives using wearable physiological sensors, what's often called the Internet of Medical Things, or IOMT.
This is a prime example of feature engineering on really complex, messy data. The data sources are physiological. ECG, galvanic skin response, which measures skin conductivity and skin temperature.
So what are the engineers actually extracting from that data?
They have to dive deep. They're looking at complex metrics from heart rate variability or HRV patterns, things like approximate entropy, which is APN, and turning point ratio, TI.
Okay, hold on. Let's contextualize those. Why are APN and TI important for stress? What do they actually represent?
That's a great question. APN and TI are nonlinear measures of the complexity and predictability of the heart rate signal. Under high stress, the autonomic nervous system gets dysregulated, and heart rate patterns often become less complex, more predictable.
I see.
So AP and TI capture these subtle shifts in HRV, and they serve as really robust computational markers for mental workload and stress. And what's fascinating is that even for this complex physiological data, a multi-layer perceptron neural network, an MLPNN, showed the highest performance.
Which just shows how effective DNNs are at capturing these nonlinear relationships.
It does. And as all these intelligent systems become massively interconnected, especially in, say, a public cloud or distributed environment, trust and data integrity become critical system requirements.
Right. If the ML model is making decisions based on corrupted data, the consequences could be disastrous.
This brings up the security architecture challenge. How do we ensure data integrity? The sources point to integrating blockchain as a kind of security watchdog for these cyber-physical systems.
We hear blockchain a lot, but what is its actual functional role here for an engineer?
Its role is immutability and verification. The raw sensor data, once it's validated, is cryptographically hashed and attached to the distributed ledger using a consensus scheme.
So once it's on the chain, it can't be changed.
It cannot be tampered with or retroactively altered. This cryptographic integrity provides verifiable trust through the whole process, guaranteeing that the ML model is making decisions on verified, trusted data.
So when you look at the whole picture of Industry 4.0, the promise is enormous, but our sources also highlight some severe challenges: the high initial investment costs, the complexity of making old and new tech work together, and of course the huge cyber threat from all this new connectivity.
Absolutely.
Yeah.
So for you, the engineer listening, the utility of ML and DL is, it's overwhelmingly clear. Models like CNNs and MLPNNs are being successfully applied to critical real-time challenges across industry, health, and security.
Sure.
But the true engineering challenge isn't just in picking the best model. It's in architecting the entire system, from that little edge device all the way to the secure cloud endpoint.
Yeah, we've focused a lot on the incredible accuracy gains, like that 98.57% with the CNN model. But the shift to Industry 4.0 isn't just about maximizing one performance metric. It's about how the synergy of AI, IoT, and cloud edge computing fundamentally restructures the entire industrial environment.
That's the bottom line. It demands a completely new level of systems design proficiency from the engineer. So here's a thought. We discussed how these intelligent systems require a sophisticated blueprint. If the smart manufacturing execution system, the system managing the factory floor, is designed to deeply reflect physical reality, capturing the precise operations and concepts of the shop floor and its structure, what new capabilities could an ML engineer unlock by focusing exclusively on defining the data model itself, rather than just optimizing the algorithms that use it? The data structure might just be the next great frontier.